Hello, STT 315. This is recitation 13. So let's get started with question 1. It's a multiple choice. So which of the following is a result of carrying out a given statistical test of hypothesis at a level of significance 5%? So the answer would be option D, which is that the probability of rejecting the null hypothesis is 5% when it is true. Question 2. In a testing problem, the p-value was observed to be 0.05. Let alpha stand for the probability of type 1 error or the level of significance of a test. Then which of the following statements is true? So the correct answer here would be that the null hypothesis would be rejected when alpha is 0.8 and also when alpha is 0.06. Next is question 3. Suppose that measurements of cholesterol level in women in the U.S. population age 21 through 40 is normally distributed with mean 52 milligrams per DL. It is desired to test if the cholesterol level among Asian immigrants is different from those in the general U.S. population. A study of a sample of 125 Asian women of age 21 through 40 yielded an average measurement of 55.09 with a standard deviation of 12. So we want to find the appropriate formulation of the testing problem. So we're going to be using a z-test, because we have a sample size of greater than 30. So we have our mu naught would be 52, which is what we believe the truth to be. And we have that the sigma equals, or our standard deviation is 12, which is given right here. Our x bar is 55.09, which is also given. And our sample size is 125. And our alternative hypothesis is that it's desired to test if the cholesterol level among Asian immigrants is different from those in the general U.S. population. So the keywords are is different from. So in other words, that means is not equal to. So that's why that's our alternative hypothesis. So what you'll do is you go into your calculator and choose the statistics option, and you would do statistical tests and choose the z-test. And you would enter in this information here by putting in stats instead of data, because you don't have a long list Excel sheet of data. You have just the statistics from the data. And then when you enter in this information, you'll get the p-value of 0.00399. Oops, I just scrolled through too many pages. Sorry. Let me go back to the top. I don't know why that happened. Okay, so now we're on to the next page, page 2. Question 4. So for an airline, the average price of tickets on the New York to Hawaii route last year was $1,580. It claims that the average ticket price has not changed in the past year. It is desired to test if this claim is correct. So in other words, we want to test whether the average ticket price has changed or not. So data on a sample of 235 tickets yielded an average of $1,584.79 and a standard deviation of $25. Assume that the price of a ticket has a normal distribution, and now we want to find the p-value of the observations. So we're going to be using a z-test again because we have a sample size of 235, so that's a large enough sample size. And we're going to enter this information in our calculator. So our mu naught would be 1,580 because that's what it was last year. And our standard deviation is 25, which is given to us. And our average is $1,584.79. And our sample size is 235. And so has not changed. So we want to see if this claim is correct. So in other words, we want to know, is mu naught different than mu? And so in other words, we would have our alternative hypothesis to be mu not equal to mu naught. And so when you put this in your calculator, your p-value should be 0.0033. Refer to the previous problem. So if alpha is 0.025, what is your conclusion for the test? So our p-values are greater than our, oh, sorry, I made a mistake. So we would reject the null, but notice, so we would compare alpha to our p-value. So our p-value is 0.0033, which is less than 0.25. So I switched the sign. So you can ignore what I wrote here. But this is correct, that we would reject the null. Okay, so our number 6. It is known that the average life expectancy of a 50-year-old man in 1945 was 55 years. In a study of 25 men aged 50 in 1945 and who had been working for at least 20 years in a potentially hazardous injury were followed until death. Their average life expectancy was 60 years with a standard deviation of 20 years. Assume that the life expectancy for a 50-year-old man is approximately normally distributed. We want to test the hypothesis that average life expectancy for workers in this industry is not equal to that of the general population. So what is the p-value of the observations? So again, if we're looking, so now we're in the t-test situation because our sample size is 25 and that is less than 30. So now we're going to use a t-test. And our alternative hypothesis is going to be that mu is not equal to mu naught, and it's right here, I highlighted it. And our mu naught in this case is going to be 55, which is right here. This is what the known life expectancy was. So that's our mu naught. Our X bar is 60, which is here. The average life expectancy was 60 years. And then with the standard deviation of 20 years, so that's here. And our sample size is 25 because it was in a study of 25 men. And so when you put that in your calculator, your p-value is 0.2234. Okay, I'm going to zoom out before I go to the next page. Okay. Number 7. According to Money, 14% of all households own stocks. An economist wants to test this claim and see if the actual proportion is different from that claimed. In a random sample of 200 families, the economist finds that 40 of the households own stocks. For the appropriate testing problem, the p-value is, okay, so here we're going to use a 1 prop C test. And our hypothesis is going to be that P is not equal to P naught. And because we have these keywords here that are highlighted, we have is different from. So in other words, that means not equal to. So our P naught is 14% or 0.14. According to Money, which is probably a magazine or a journal. So that's what was believed to be true. And our sample size in a random sample was 200. And the economists found that 40 of the household owned stock. So here, our successes, our number of successes, or our X would be 40. So when you put that in your calculator will give you the p-value of 0.0147. All right, next is, it is believed that the fraction of defective items among a large shipment of a certain kind of product is 0.12. So that's what's believed to be true. After some changes have been made in the production process, the manager now wishes to test if the fraction of defective items has gone down. A random sample of 625 products has 65 defectives. So what is the p-value of the observations? So here we have a 1 prop z test again, because we have a sample size of 625. So that's a large enough sample size. And our p naught is 0.12. And here our X, the number of successes, which I know it's kind of confusing because we're talking about defective, but our X would be 65. So in other words, if it's defective, in this case, it's considered like a success. So anyways, so X is 65 because there were 65 defectives in that sample. And our alternative hypothesis is that P is less than P naught, because we want to wish to test if the fraction of defective items has gone down. So if we want to test that, then we want to test if our P is less than what we thought was true, our P naught. So when you enter this in your calculator, your P value will be 0.1092. So to kind of summarize, when I go through these questions, I always want to look for the keywords when I'm trying to decide what my alternative hypothesis would be. Am I having words that say has gone down, or less than, or greater than? Or am I going to be in the not equal case where I have keywords like is different from, or if I look in the previous pages, where is it? Sorry. The previous page is different from, has not changed, is not equal to. So all of those keywords would imply that our alternative hypothesis is, we would have a not equal to symbol opposed to a strictly less than or strictly greater than. So those are some keywords to look for when you're approaching these problems. All right, now I'm going to go over the past homework. And a lot of these these homework problems were similar to, if not the same to, recitation 12. So the previous recitation, and possibly recitation 11. So let's get started with this. So following is a random sample of the year 1986, or from the year 1986, of person incomes of industry workers in the state of New York in thousands of dollars. So we have 19.9, 17.8, 19, 13.9, and the rest of the numbers, I'm not going to read them. And then what is the point estimate of the mean? Okay, so to find the point estimate of the mean, we're going to add up all of these numbers and divide it by the total. And our total here is 12 in our sample. So we have, if you add all of them up, I didn't write out all the numbers because it would just be overwhelming to look at. But if I wrote down all of them, added them together, divided them by 12, you would get 16.23. You could also use R in this situation, enter it into a list, and then you would just do the mean function of whatever you called that list to be, and you could find it. And then what is the point estimate of the standard deviation? So you could do this in R and do the function SD and then parentheses what you called that list to be, or you could do it brute force by hand, and that would look like this. So you would take each xi, so let's say we take the first xi, so x1, which is 19.9, subtract the mean, which we had found in the previous question, and then square that, and then add that to the next, using the next the next sample point, which is 17.8, and then subtract that from the mean, square it, and add up all of those all the way through 16.1. And then you're going to divide that by the total, which is 12, and then take the square root of that number altogether. And when you do that, you'll get 2.45. So for this, it's fastest to use R, but I like writing this out because it just helps with understanding of how to calculate the standard deviation. Okay. A market research worker interviewed a random sample of 18 people about their use of a certain product. The results in terms of Y or N, for yes, a user of the product, or no, not a user of the product, are as follows. So we have Y, N, and so on and so forth. And we want to estimate the population proportion of users of the product. So yes means you're a user of the product. So to find that proportion, we want to find the number of Ys and divide that by the total, which is the number of Ys plus the number of Ns. So if you count up the number of Ys, we have 1, 2, 3, 4, 5, 6. And then if you count up all of these, or they give you also the total here, that's 18. So you would get 6 divided by 18 as the population proportion of users of the product. Okay. This question was in the previous recitation, but I'll still go over it in case if there are some slight differences. I know the numbers here are different. So on a given day, the average price per share on the Big Board Composite Index in New York rose 20 cents. Assume the population standard deviation that day was 7 cents. If a random sample of 50 stocks is selected that day, what is the probability that the average price in this sample was a rise between 18 and 22 cents? So here, if we write out just what we're given, our sample size is 50, our standard deviation is 7, and our X bar is 20. And so we want to find the probability that our X bar lies within 18 and 22. So if I wanted to visualize that, we want to find the area under the curve from 18 to 22. So we're going to use our normal CDF function. And our lower bound is going to be 18. Our upper bound is going to be 22. Our mean is going to be 20. And our estimate of the standard deviation would be the standard deviation divided by the square root of n. So we would have 7 divided by the square root of 50. So when you put that in your calculator, you'll get 0.956648, which rounds to 0.9566. Okay. I believe this question was also in a previous recitation. So Mercury makes a 2.4 liter V6 engine used in speedboats. The company's engineers believe that the engine delivers an average power of 2,230 horsepower, and that the standard deviation of the power delivered is 129.8. A potential buyer intends to sample 52 engines, each engine to be run a single time. What is the probability that the sample mean will be less than 2,185 horsepower? So we want to find the probability that our X bar is less than or equal to 2,185. So we'll have the normal CDF function, and if I wanted to draw it out because I like pictures, here our mean was given to us as 2,230, so that's in the middle of that curve, and 2,185 would lie somewhere to the left of that. So we want to find the probability that X bar is less than 2,185, so that would be the area under the curve that's shaded, because that's less than that. So we would do normal CDF, and our lower bound is going to be negative infinity. In other words, negative 10 to the 10, all the way out here. And then we'll move to the right, and our upper bound will be 2,185. And then our mean is 2,230. And when we go through the standardization process, our standard deviation is going to be our sigma, which is 129.8. That was right here, the standard deviation of the power delivered, divided by the square root of our sample size, and our sample size was 52 given here. So we'll get 0.00621. Okay. When sampling is done for the proportion of defective items in a large shipment, where the population proportion is 0.07 and the sample size is 200, what is the probability that the sample proportion will be less than 0.09? I believe this question was also in a previous recitation. So we want to find the probability that P hat is greater than or equal to 0.09, because that means at least 0.09, so it could be 0.09 or greater than that. And so we would do normal CDF, and our lower bound is going to be 0.09, and our upper bound is going to be infinity. And then we would have P, and then the square root of P times 1 minus P divided by N. So when we plug in what we know here, our P is going to be 0.07. That's the population proportion. And then here we would have 0.07 times, and then 1 minus P is 0.93. And our sample size is 200. So that equals 0.133. My calculator said 813, but my calculator sometimes automatically rounds more than I want it to. But it's the closest option to what is correct, which is 0.1335. So some of the questions that we're about to go over, my rounding is a little bit different, but I think that's because my calculator automatically rounds sometimes more than I want it to. And I haven't figured out how to change that setting. Okay. Abe and Betty want to estimate the mean of a population with known standard deviation, sigma. Abe takes 50 samples, whereas Betty takes 80 samples. Which of the following statements are correct? So we want to keep in mind that Abe took less samples than Betty. So the correct statements, I'm just going to say, because I don't want to get the wrong ideas in your head, are if both Abe and Betty use confidence intervals of the same width, then the confidence level of Abe's interval is smaller than Betty's. And remember, that's because Abe has less samples than Betty. But here, this is also true. If Abe and Betty construct confidence intervals with the same confidence level, then the width of Abe's interval is larger than that of Betty's. And that's also because Abe has less samples than Betty. All right, moving on. That's the next question is kind of similar. However, now the standard deviation is going to be different. So Abe wants to estimate the mean of a population with standard deviation 10. Betty wants to estimate the mean of a population with standard deviation 20. So Abe has the smaller standard deviation than Betty. If both of them take the same number of samples, then which of the following statements are correct? So it would be these two statements. So if both Abe and Betty use confidence intervals of the same width, then Abe's confidence level is larger than Betty's. And that's because Abe has the smaller standard deviation. And then here, this is also true. If Abe and Betty construct confidence intervals with the same confidence level, then the width of Abe's interval is smaller than that of Betty's. Okay. Next. So which of the following has the smallest margin of error? So when we look here, for the margin of error calculation, so n is in the denominator. So if we want a small margin of error, we would want a large n. We would want a large denominator. And k is in the numerator. So in k, a smaller confidence level would mean that we have a smaller k. So because k is in the numerator and we want a small margin of error, we would want a smaller confidence level. So we want to find, okay, what has a large n and a small confidence level? So that would be this option here. We have a large n of 450. And so if we look at first just which one has the largest n, so we're in these two options. And then if we compare these two options together, the first option has the smallest confidence level. Okay. An insurance company handling malpractice cases is interested in estimating the average amount of claims against physicians of a certain specialty. The company obtains a random sample of 169 claims and finds X bar equals $17,060 and S equals 5,572. Give a 95% confidence interval and a 99% confidence interval for the average amount of a claim. Okay, so here we have our N is 169. Here, I'll scroll back up. 169. Our X bar is 17,060. Our S is 5,572. And we want to find a 95% confidence interval and a 99% confidence interval. So here, I just went through the different steps for each level of confidence. So for the 95% confidence interval, if we want to find our K, we're going to do the inverse norm of 1 plus 0.95, which 0.95 comes from the confidence level we want, and then divided by 2, and then we would have 0 as the mean, and the standard deviation is 1. And so that gives us a K of 1.96. And for the 99% confidence interval, we would have a 99.99 here instead of a 0.95, which would give us a K of 2.576. All right, so now we need to find our M, so our margin of error. So that's K times sigma divided by the square root of N. So here, for the 95% confidence interval, our K was 1.96. Our sigma is 5,572, and we divide that by the square root of N, which is 169. So our M equals 840.086 for the 95% confidence level. Now we want to find our M for the 99% confidence level. So here, what's going to change is our K. So our K is 2.576, and then we have the same sigma and the same sample size here. And our M for the 99% confidence level is 1,104.11. All right, next is the actual calculation of the confidence interval itself. So we're going to do X bar minus M to get that lower bound of the confidence interval, and then X bar plus M to get that upper bound of the confidence interval. So for the 95% confidence situation, we have our X bar minus M is 17,060, which was given to us in the problem, and then minus our M, which we just calculated in the previous step here, which gives us 16,219.9. And then when we do X bar plus M, we get 17,900.1. And if I scroll up, that answer here, so our lower bound matches. And like I said, my calculator rounds, so my calculator rounded this as a 0.9 and my calculator rounded this as a 0.1. And then for the 99% confidence interval, we would do X bar, which is the same as before, so 17,060 minus our M, but our M is different in this confidence level, so our M is 1,104.11, and that gives us 15,955.9. And then we would do X bar plus M, which gives us 18,164.1. And like I said, my calculator rounds, but it's gave the closest answer to the correct answer, which is 15,954.7 to 18,165.83. Okay. Next. Right. In a survey conducted by a firm, a sample of 80 residents in two-story home, in two-story homes, 40 were found to own their own houses, or found to own their houses. Find a 95% confidence interval for the proportion of residents of two-story houses who own their house. Okay, so here we're going to have to do our p hat first. So our p hat is 40 divided by 80, because we have 40 that own their houses out of the 80 residents. So 40 divided by 80 equals 0.5. Our K is going to be, well, we have a 95% confidence level. So when we do the inverse norm of 1 plus 0.95 divided by 2, and then a mean of 0 and standard deviation 1, we get 1.96. And then our margin of error is going to be K times the square root of P times 1 minus P divided by N. So we already calculated K, we have our P, and our N is given to us. So we can plug and chug. So our K is 1.96 times the square root of, so our P was 0.5. So our 1 minus P is also 0.5. And then we're going to divide that by our total number of residents in our sample, which is 80, and we'll get 0.109567. Now it's time to actually calculate our confidence interval, because we have our p hat and we have our M, which we just found. So we have p hat plus and minus M. So that would look like our lower bound would be 0.5 minus 0.109567, and our upper bound would be 0.5 plus 0.109567. And when you calculate this, it equals the correct answer in bold. Next is the firm came up with a confidence interval of 0.3698 to 0.6302 for the proportions of residents of two-story houses who own their house. What confidence level did the firm use in percent? Okay, so here we kind of have to work backwards. So we're given a confidence interval, and we want to find what is that confidence level. So working backwards, we know our confidence interval equals p hat plus and minus m. So if we take, you can either work with the lower bound or the upper bound. So I just worked with the lower bound, but either way you'll get the same answer. So the lower bound equals our p hat minus our m. So our p hat is 0.5, and then our m is unknown right now, and because we don't know what our k is, which is in our m, and we don't know our k because we don't know our confidence level. So we first want to find our m, then we'll find our k, and then we'll find what that specific confidence level is. So when you have this equation here and you solve for m, we would subtract 0.5 from this number, and then divide it by a -1 to get m equals 0.1302. Okay, so now we know that our m, to find our m, the formula equals k times p times 1 minus p divided by n, or k times the square root of that. So we just found that our m is 0.1302. So we'll just set that number equal to this expression. And if we plug in what we know in the expression, that will make our lives easier. So our p is 0.5. So our 1 minus p is 0.5, and our sample size is 80. So if you take this equation here that I'm circling with the mouse and solve for k, we're going to take this number here, 0.1302, and divide that by the square root of 0.5 times 0.5 divided by 80 to get our k, which equals 2.32909. All right, so now we have our k. So now we have k, which is what we just found here, 2.32909. That equals the inverse norm of 1 plus our confidence level, which we don't know, divided by 2. And then, mean 0, standard deviation 1. So now we need to kind of be clever. And so, in other words, we have, if we were to draw out what we know, and I'm going to zoom in a little bit to make it easier to see. I know it's a lot to look at, but we have our density here, our standard normal density. So we have our mean 0, standard deviation 1, and our k is over here, which we already know, that's the 2.32909. So that's to the right of 0. And now we want to find what is this area under the curve. So we're going to do normal CDF with our negative, or with our lower bound to be negative infinity, our upper bound to be the k, which is 2.32909, and then our standard, or mean 0, standard deviation 1. And when you do the normal CDF in your calculator, you'll get the area under the curve to be the area under the curve left of k. So here is going to be 0.990073. Okay, so we know that that number is going to equal what's inside here, the inverse norm. So that equals 1 plus our confidence level, which is unknown, which is the question mark, divided by 2. So now we're just going to solve algebraically for this question mark. So we're going to multiply this number by 2 and then subtract 1. And so we'll get 0.980146, and that is our confidence level. So if I zoom out, we get that confidence level of 98.02 if we round. Okay, next is the firm requires a 95% confidence interval with width 0.1096 for the proportions of residents of two-story houses who own their house. What is the required sample size? Assume nothing is known about the population proportion of residents who own two-story houses. So these keywords here always mean that we'll be using, when we have P, it'll be 0.5 when we assume nothing is known about the population. So here we have our formula for N, our sample size, which is, or the required sample size, which is K squared times P times 1 minus P divided by M squared. So our K squared is going to be 1.96 squared, because we have a 95% confidence interval. So we already found what would happen if we had a 95% confidence interval. Our K is 1.96. And then because nothing is known about the population proportion, we're going to do 0.5 as our P, and then 1 minus P is also 0.5. And then we would divide that by our M squared, which is, where is this? 0.1096 here, our width, 0.1096 divided by 2 squared. And so the reason why we divide this by 2 is our M is half of our width, because when we do a confidence interval, we take our point estimate or our P hat plus and minus our M. So that means our total width of the interval is going to be, we're gonna add M, so we have M here, and then we have M on the other side, so it's like M times 2. So since we have the width and not M, we are gonna divide that by 2. So, and M being the margin of error. So when you calculate this, you'll get 319.809, and then you always round up. And so, because we can't have a fraction of a person, a resident, so we get 320. All right. A newspaper agency wants to estimate the proportion in a population who will buy their new news magazine using a 70% confidence interval. Information from sale of similar magazines suggests a prior guess of 0.1 for the proportion. How large a random sample would be necessary for the interval to have a margin of error of 0.025 or less? Okay, so here we have a 70% confidence interval. So if we want to find our K, we're going to do inverse norm of 1 plus 0.7, because this is our confidence level here, divided by 2, and then mean 0, standard deviation 1. So our K is 1.03643. And then if I'm just writing what was given to us, we have our P is going to be 0.1, because that's our prior guess for the proportion. And our margin of error is going to be 0.025 or less. So to calculate the sample size that would be necessary, it's going to be K squared times P times 1 minus P divided by M squared. So we found our K here. We're going to square that. And then our P is 0.1. And then 1 minus P. So 1 minus 0.1 is 0.9. And then divide that by the margin of error squared, which is 0.025 squared. And you'll get 154.683. And if you round up, the closest correct answer is 156. Next. A real estate agent needs to estimate the average value of a residential property of a given size in a certain area. The real estate agent believes that the standard deviation of the property values is 5,925, and that property values are approximately normally distributed. A random sample of size 25 units gives a sample mean of $88,574.58. Give a 95% confidence interval for the average value of all properties of this kind. Okay, so I'm just going to write down what we're given before we jump into the problem. So our sigma is 5,925. That's given here. Our sample size is 25. Our X bar, our sample mean is $88,574.58. We want to give a 95% confidence interval. Okay, so now we're ready to jump in. So our K is going to be, for a 95% confidence level, is going to be 1.96. Our M is going to be K times sigma divided by the square root of N. So our K is 1.96. Our sigma is here, 5,925. And then divide that by the sample size, which is 25. And we'll get 2,322.6. So we have our X bar, which is given, and we just calculated our margin of error. So now we're ready to compute the confidence interval by doing X bar plus and minus M. So when we do that, we have, so our X bar is given here, our M is here. So our lower bound, my calculator gave me 86,252, and my upper bound is $90,897.20. My calculator rounds automatically, so it rounded this number to, rounded it up. And then it also rounded this 0.18 to 20. But if I look, this is the closest to all the options. That's correct. Okay. All right, I believe this question was in a previous recitation, but we will still go over it. There may be some slight differences though. So Beechcraft Incorporated wants to estimate the average time it takes the Beechjet Corporation jet to climb from sea level to 41,000 feet. From previous experience, company engineers believe that the standard deviation of climbing time is 3.5 minutes. The model is tested in 100 random trials, and it is found that the sample mean is 23.5 minutes. Give a 95% confidence interval for the average climbing time from sea level to 41,000 feet. Okay, so our K is going to be 1.96 because we have a 95% confidence interval. Our M, our margin of error, is K times sigma divided by the square root of N. So our K is 1.96. Our sigma, or standard deviation, is 3.5 minutes. So that's here. And then divided by the square root of N, and our sample size is 100 random trials. So that's a 100. So our M is 0.686. So our confidence interval is X bar, which is 23.5. That's our sample mean, plus and minus that 0.686, which is our margin of error. So when you subtract, you get 22.814. And when you add, you get 24.816. All right. A tire manufacturer wants to estimate the average number of miles that may be driven on a tire of a certain type before the tire wears out. A random sample of 32 tires is chosen. The tires are driven on until they wear out, and the number of miles driven on each tire is recorded. The data in thousands of miles are as follows. Okay, so here's our list. Here's our data. So give a 99% confidence interval for the average number of miles that may be driven on a tire of this kind. Okay, so here, this is similar to the previous recitation, but if I remember correctly, the previous recitation may have had a smaller sample size. But anyway, so just to calculate some things off the bat before we jump into our confidence interval, I want to know my sample size, I want to know my sample mean, and I want to know my sample standard deviation. So our sample size is 32, which is given here, or you can count the number of numbers that were given. And then our X bar is going to be, you add all these numbers together and divide it by 32. And that's here, which is 29.75. For me, it was faster to use R. So my R code looked like I just labeled this list of numbers as T. You can label it whatever you want. And so I made a list. So I did C, open bracket, and then I listed all of these numbers. And then I used the function mean of T, which is this list, to get the mean. And then I did the same thing for standard deviation R, which is the function SD, and then I put T here. Or you could do it brute force. So you would do the sum of your xi's minus the X bar squared divided by our sample size minus 1. So our standard deviation, our sample standard deviation is 5.702292. And right off the bat, I'm gonna see what my K is for a 99% confidence level. So inverse norm of 1 plus 0.99 divided by 2 gives us our K of 2.576. Okay, so now I have what I need to calculate the margin of error M. So M equals KS divided by the square root of N. So our K is 2.576. Our S is 5.702292 divided by that square root of N, which is square root of 32. And so we get 2.59669 as our margin of error. Now we can calculate that confidence interval. So we would do X bar plus and minus M. So our X bar we calculated to be 29.75, and then plus and minus that M here, which we just found. So when we subtract, we get 27.1533. And then when we add, we get 32.3467, which is what the correct answer is. An airline wants to estimate the proportion of business passengers on a new route from New York to San Francisco. A random sample of 364 passengers on this route is selected, and 199 are found to be business travelers. Give a 90% confidence interval for the proportion of business travelers on the airline's new route. Okay, so I'm going to calculate my P hat. So my P hat is going to be 199 over 364 because we have 199 are found to be the business travelers out of a total of 364 passengers. So that equals 0.546703. So that's our P hat. Now we can find our K, which we want a 90% confidence interval. So we would do the 1 plus 0.9 divided by 2 when we do our inverse norm. So we get 1.645. That's our K. Now we have what we need for our margin of error, which is K times the square root of P times 1 minus P divided by N. So our K is 1.645, and then the square root of of P, which is given here. And then this number here is 1 minus 0.546703. So we get this divided by 364, which is our sample size. And that's the total number of passengers. So we get our M to be 0.042922. Now we can calculate the confidence interval because we have our P hat, and then we'll do plus and minus our M. So when we, so our p hat's the 0.546703, and then our m is the 0.042922. So when we subtract, we get 0.5037, and when we add, we get 0.589625, which my calculator rounds a little differently. So the closest answer, or this is closest to the correct answer. Okay. Find the minimum required sample size for estimating the average return on investments of a certain kind to within 1% per year with 90% confidence. The standard deviation of return is believed to be 7% per year. Okay, so 1% is our margin of error. And now let's find our K. So that's going to be inverse norm of 1 plus 0.9, because we have 90% confidence, divided by 2. So we get 1.645. And then our standard deviation is going to be, so here it's believed to be 7%. So it would be 0.07. And our N is going to be greater than or equal to K squared times sigma squared divided by M squared. So our K squared is the 1.645 squared, and then we'll have 0.07 squared, and then divide it by the margin of error squared, which we said was 1%. And so we get 132.595, and then we round up, and then the closest answer to this is 134. And I believe that concludes this recitation. I hope that was helpful.